work for an organization called the AAVSO, the American Association of Variable Star Observers. They're based in Cambridge, Massachusetts. And you can, with a little experience, establish brightnesses of stars, magnitudes of stars, by comparing them to stars with known magnitudes. This is a program quite a few people are engaged in and have been for many, many years. It's an international endeavor. And the findings that you make as you watch variable stars, because stars vary in brightness, these findings, properly noted, are then returned periodically to Cambridge, and they are charted today by computer, and they give professional astronomers a great deal of information about the behavior of variable stars, which they themselves, the professional astronomers, do not have time to make. These observations best done by amateurs. And the Problicom program, of course, which works with very nominal equipment, equally employs the time and talents of amateurs with very, very little investment by using plain photography to achieve similar ends. In fact, the American Association of Variable Star Observers has now asked me to participate in their NOVA search program, which is a part of the AAVSO. NOVA being a variable star, the very fact that it explodes makes it a variable. It varies very quickly, in fact, when it first bursts into view. The Problicom program is, I feel, a program, the time of which has come, and one that addresses itself particularly to the beginning amateur who doesn't know what's there and what should be where, but who can, by just noticing something new, then find out what it is, get counsel, and make potential discoveries.
Today, almost any reddish star seen in the night sky is a red giant. Antares, in the constellation Scorpius, probably was much like our sun at an earlier time in its evolution. But in becoming a red giant, Antares increased its volume to some 60 million billion times the volume of our sun. A star becomes a red giant when the hydrogen in its center becomes depleted, causing the core to collapse under gravitational pressure. The energy produced during this collapse radiates outward, causing a phenomenal expansion of the outer part of the star. But even the red giant phase is not the last phase of a star's life.
The star leaves the giant region essentially in two ways, either peacefully or violently. The peaceful end of its life is a contraction to a white dwarf. The violent end is more complicated. The star gradually exhausts all resources of energy it has. Then it begins to collapse suddenly, but the heating of the innermost layers is so strong that the star eventually explodes in the form of a supernova, throws most its material into space, and the remnant becomes a neutron star or a black hole. Now the decision which way it will take depends on its instantaneous mass. If the mass is sufficiently small, smaller than about 1.4 solar masses, it will become a white dwarf. If the mass is larger, then the star should in principle explode. However, it is possible, and in most cases it probably happens, that before the decision is made, it can shed most of its material, so actually probably stars up to, say, 7 solar masses can still become white dwarfs, provided they manage to get rid of most of their material at the red giant stage.
When, as a red giant, the sun's supply of nuclear fuel is eventually exhausted, and the temperature at its core is insufficient to release more energy through the fusion of still heavier elements, the sun finally loses its relentless battle against gravity. Decreasing in size and in brightness, the sun will enter its last phase and become a small white star. Only 1/100th the size of our present sun, this white dwarf will begin the long, slow process of burning out. Nearly invisible, it will wander through space. The only energy remaining is that which formed it, gravity.
You know, in many public lectures, my colleagues usually call white dwarfs dead star. I think it's unfair. They are simply retired stars. They no longer produce new energy, but they have kept enough of heat inside. Now they are much thriftier in emitting that than before. Therefore, they gradually cool off. They also gradually become fainter and fainter, but at this stage they can live for tremendously long ages, for billions of years. And they gradually become less white and more reddish or gray and so on. In the end, they must be really dark stars, very cold, emitting no light, but they are still there. Nothing can, as far as we know, nothing can destroy them. But their lifetime may well be longer than the lifetime of our whole stellar system.
Some stars do something very pretty as they evolve. They become planetary nebulae. This is a peculiar and odd name, and it's an indicator when these objects were first discovered, they really weren't recognized for what they truly are. In the late 1700s, after William Herschel had discovered the planet Uranus as a small greenish disk in his telescope, an appearance which was matched closely by the planet Neptune, discovered about half a century later, well, astronomers combed the sky looking for more of these small blue-greenish disks in the hopes of finding more planets. Well, they found quite a few of the blue-green disks, but they didn't find many more planets at all. And they realized fairly soon that the disks that they did find weren't planets. They actually looked more like clouds of gas or nebulae in space. They didn't move like planets either. Still, there was this superficial resemblance to Uranus and Neptune, and so these objects were called planetary nebulae, even though they have absolutely nothing to do with planets. They're actually bubbles or shells of gas that have been gently thrown off by stars of low mass late in their lives as a kind of a final gasp before cooling off and fading. These planetary nebulae have picturesque names, too. Names like the Ring Nebula, the Helix Nebula, or the Dumbbell. And they clearly look like bubbles or smoke rings with the remnant of a star in the center that is a collapsed, dense heap.
A planetary nebula is probably exactly the case when a star originally has an excess mass for a white dwarf, but manages to shed it at the stage of a red giant. If you imagine a star which is not too massive, say like our sun, or 2 solar masses or 3 solar masses, when it has expanded to the giant and red giant stage, it's an enormously expanded star, which if it were in the place of our sun, it would actually have its surface beyond the orbit of Mars, say. It's natural that the gravitational attraction of the star upon its surface is really not too strong when the star is not too massive. It's possible that the outer layers can escape into space. If they are blown away into space, but not too violently, they can form a shell surrounding the star, a shell of gas, which is visible for some time as a planetary nebula. Planetary nebula is a relatively peaceful release of the outer envelope of a star into space. What's left is the central hot star. In fact, it's already a ready-made white dwarf sitting there inside a giant star. Now, it must cool off a little bit, so there is still a certain evolution, but gradually, probably the central stars will be transformed into ordinary white dwarfs.
The planetary nebula phase through which some stars pass is a very brief phase, lasting only a few tens of thousands of years. The planetary shell provides one means by which a star can shed some of its mass and evolve from a red giant into the final stage of its existence as a white dwarf. A more complex but equally interesting situation arises when a star is orbited closely by another companion star. Then it's actually possible for gaseous material to be passed from one star to the other.
When a star has another star very close to it, in other words, if it is a double star, or as we say most of the time, binary star, There